G'day everybody. In our lesson today we're going to start talking about continuous probability distributions. So we call these probability density functions. So we'll find out in this lesson how we represent probability distributions for continuous variables. We'll see that calculus gives us the tools to calculate probabilities in these types of functions. Like we have in discrete distributions, we'll find that we can calculate an expected value and other measures of central tendency, like the mode and the median of the distribution. And as well as that, we'll calculate standard deviations or variance. So just a bit of a definition about probability density functions. They map a random variable in such a way that the area under a curve is the measure of the probabilities associated with that variable. So we'll have some sort of curve. As we'll see in the example in this lesson, often it's a piecewise or hybrid function. In this case, this diagram is a continuous function. Our variable, our random variable, is represented along the horizontal axis. So if x is a random variable, then the probability that the outcome of that variable will be between a and b is equal to the area under the curve. In other words, using integral calculus will give us the tools that we need to calculate probabilities associated with these types of functions. A couple of properties, very similar properties to that of discrete distributions. The function will be positive for all values of x because each point on that curve is an indication of the probability associated with the variable x, which is always positive, and because it represents a complete distribution, the total area under the curve, either from negative infinity to infinity, will be equal to 1, but we'll also see that sometimes PDFs, probability density functions, might really just be defined between two boundaries, a lower boundary and an upper boundary. You might want to pause this screen and write down a few of these formulas. We've got a formula for the mean or the expected value of a continuous random variable. It's an integral from a to b, or from negative infinity to infinity, not of the function but of x times the function, which sort of mirrors that formula in discrete distributions where we multiply each value of x, each discrete value of x, with its associated probability. We can calculate the median of a distribution by solving some value m, so that the area under the curve from the lower boundary to m is exactly 1/2. Alternatively, it might even be easier to, depending on the function, to set up an equation where the area is from m, the median, to b, the upper boundary of the curve as well. In a distribution like this, if there's a particular maximum value of f, then that value of x is an indication of the mode of this distribution. So they are the three measures of central tendency: the mean, the median, and the mode. We have a formula here for calculating the variance, which is the integral of x squared times f of x minus the mean squared. So we'll see how we calculate that. And then the variance, when we take its square root, that will give us the standard deviation of the distribution. So we're going to look at a particular example of a PDF, and you'll find that in this lesson most of the work that we do will be on a CAS calculator. So here's a probability density function. Let's take a look at a few of the features. This one does have a lower and upper boundary, so between 0 and 6, that's where all of the values of the random variable will have a probability greater than 0. For all other values outside those boundaries, the value of the function is 0. And so this function has been defined with a hybrid function. So we can see the two major parts. We've got a quadratic section, which is this part of the hybrid function, and we've got a linear section, which is the second part of that. Between 0 and 2, and between 2 and 6, and then the function is 0 for all other values of x. And because it's a probability density function, we know, or we could even demonstrate, that the area underneath this curve between 0 and 6 is exactly equal to 1. You can see here we have narrowed the interval from x equals 1 to x equals 4. That gives us an area of approximately 0.7813. And so that's an indication that the probability that x lies between 1 and 4 will be 0.7813. That particular probability could be calculated without a calculator. We've set up integrals here. We've got the quadratic part of the function, the linear part of the function. So the area that we've shaded in this PDF is the integral from 1 to 2 of the quadratic part. Add to that the area from 2 to 4 of the linear part of that function. That will give us also the value 0.7813. And here is exactly the same calculation, but with the CAS calculator. So you can see that I've set up the hybrid function, defined it on the calculator, and then calculated the area from 1 to 4, or the integral from 1 to 4, and we get exactly 25 over 32, which is equivalent to 0.7813. This particular probability density function has a maximum value right here at the coordinates 2 and 3/8. So that's an indication that the mode of this distribution is 2. This value of x is what gives us the mode. So the point on the function that has the highest probability associated with it. Keep in mind, depending on the type of function, if it's a smooth continuous function, sometimes that mode occurs at a stationary point, and so calculus could be used to find the mode that way. We might actually be using differential calculus to locate a stationary point, and thus we would find the mode for that function. Let's have a look at the mean or expected value. So here was our formula for the mean. So we've got the integral of x multiplied by the function f of x. Here that has been performed with the CAS calculator. So the integral from 0 to 6 of x times f of x is approximately, or maybe exactly, 2.875. Here we are finding the median. You can see in the diagram I've shaded half of that area and indicated that the point at which those two areas are separated is when x is equal to m, and that will be our median value. So I've set up the calculator to solve an equation for m. So we're solving for the variable m, where m is the upper boundary of the integral from 0 to m of the function, and that's exactly equal to a half. The calculator, we had to force that to give an approximate value, So in this case, I've solved that the median is approximately 2.73. That would be the median value of the distribution. If I don't use the hybrid function but actually use the linear part of the hybrid function and solve m from as an integral from m to 6, in this case the calculator handled that quite well, and we get an exact value for the median value of x, obviously still 2.73. So the median being the ability to say that the probability that x is greater than or less than 2.73 is exactly 1/2. And on this screen here, I'm using the CAS calculator to find the variance and the standard deviation of this distribution. Up the top here, I've shown the formula for the variance. So we've got the integral of x squared times f of x minus the mean squared. So on the calculator, I've calculated the mean here, 2.875. And then finding the variance, we've got an integral from 0 to 6 of x squared times f of x minus the mean squared. I've copied and pasted that calculation for the mean in brackets squared, and we get a variance of approximately 1.33. Taking the square root of that value, we arrive at the standard deviation of the distribution, approximately 1.16. And so we can find the measures of spread for this distribution. So that completes the lesson. We've looked at how we represent probability distributions for continuous variables by using PDFs, or probability density functions. We've used calculus with and without the calculator to calculate probabilities, also to solve the median. We've used the calculator to find the expected value, or the mean, of the probability distribution, and we have formulas for calculating the variance and the standard deviation. So please write down any questions you have, complete the Google form to log your attendance and to check your understanding. Thanks very much.